Okay, Mr. Smith here, and we are talking about solving this rotational equilibrium problem. And when we do this, we've got to identify and kind of draw out, make a little picture to help us solve this. I've got the picture here, so that'll kind of help me get started. But we do need to identify a pivot point. I'm just going to put this fulcrum at the middle of the seesaw as my pivot point. It turns out if something's not rotating, we can choose whatever point we want to, but this will be the most convenient point for us right now. We also need to draw in some forces. So let me change my color here. We'll draw a force for this garbage can, and that'll be this force of gravity straight down, and that's going to be 100 newtons for that 10 kilogram garbage can. We'll have a force of gravity for this fire extinguisher, and that'll just be 50 newtons for the 5 kilogram fire extinguisher. We'll also have another force of gravity for this other fire extinguisher. I'll just put it on it right now, but we'll have to decide where that goes. That's kind of the problem. Where should we put this fire extinguisher so that everything balances out? Okay, and so we now need to measure some distances. Remember that torque is RF sine theta. Okay. And so this R is called the moment arm. That's the distance between the point of rotation right here and where that force is going to be applied. And so for this garbage can, that is just going to be 1.25 meters. R equals 1.25. Okay, so from the point of rotation that we've chosen to this force that's being applied on this bar, that is our R value. And so now we can calculate what the torque is from that garbage can. That torque is just going to be the force times the distance times the sine of the angle. With these angles, that is going to be 90 degrees, and the sine of 90 is just 1. So we can actually, for all of these forces, kind of realize that the sine of the angle is just going to be 1, and we can leave it off of our equations. The same thing with this fire extinguisher over here. The distance we know already, that is going to be 0.5 meters. So we'll draw that in here. R equals 0.5 meters. And we could calculate its torque now as well. And this fire extinguisher, we don't know where that's going to go yet. I'm going to maybe make this a different color when I draw this in, just to kind of highlight that we don't really know how far this is going to be. I'm just going to put that line in right here, and we'll just put a R equals question mark. We're not sure where that's going to be placed. That R is what we're going to try and solve when we actually make this equation. And so wherever that is, it's going to have a force down of 50 newtons, but we're not exactly sure where that force is going to be yet. And so with all of these problems, remember the torque that we have in the clockwise direction or the counterclockwise direction has to equal the torque that we have in the clockwise direction. All right, so torque counterclockwise, anything trying to make this spin kind of this way, and the torque clockwise, anything trying to make it spin in the other direction, they're going to balance out if it's in rotational equilibrium. So this garbage can right now is trying to make this whole teeter-totter twist like this, and these fire extinguishers are trying to make it twist in the opposite direction. And so those kind of torques have to balance out if it's not going to start rotating one way or the other. So our counterclockwise torque is coming from this garbage can, and that is going to be again, RF sine theta. Again, the sine of the theta is going to be 1, sine of 90 is going to be 1. And so here we have R is 1.25 multiplied by the force of 100 newtons. And that's going to equal the torque from this fire extinguisher in the clockwise direction, which is just going to be 0.5 multiplied by 50 newtons. Okay? And then we're going to add on the torque from this fire extinguisher, even though we don't know where it's at yet. It's going to be some distance from the pivot times its force, so times 50 newtons. Okay? And that's our equation. This would be 0.5 meters, this would be 1.25 meters, put some units on. And then it's just solving the equation. So this would be 125 Newton meters of torque in the counterclockwise direction. This one is going to be 25.5 times 50 Newton meters in the clockwise direction, plus whatever our R times 50 is. So I'll subtract over the 25, divide by 50, and I get a distance of 2 meters. And so if we did this right, we should be able to place that 2 meters away from that pivot point. I've got this all over here, so let's try that. If we take this and place it 2 meters away, I take those things away, and voila, it balances. If it wouldn't balance, if I take that out, for example, it twists one way or the other. If I move this in too far, it doesn't balance. Okay, but we calculated that it should be exactly at 2 meters, and it works. So play around a little bit with this simulation, and hopefully this kind of makes sense and the equations make sense, and let me know if you have any questions.